Inverter topologies for mainly industrial drives and grid-tied applications. But if you see in literature, you can see many topologies, a lot of multi-level topology, inverter topologies reported in literature across the world from R&Ds and industry. But still, if you say the industry, practical application, they use either 2-level or 3-level. Surprisingly, I noted that one, especially motor drives application. The 3-level is the most popular in still the medium voltage drives application. And if you see the superfast train by the Shinkansen, I found still they are using their own old 3-level or the variants of the 3-level for their drives application. But many topologies are available. Interesting topologies are reported from industries and academia, but research has to continue. So here what I am proposing is some of the topologies we propose from this lab through my research students and verified through laboratory prototype and published work, which I will be talking here. So before power electronics converters. These are some of facilities. It facilitates efficient control and conversion of electric power. You have the power control with power devices and other computing power available. Fast control, easy control of power is possible. Then minimize the losses and achieve high efficiency in energy conversion. Devices with low on state, we can go for high frequency switching. So many of the inverters can go for high efficiency up to more than 90 is possible nowadays, 94, 95. These are some of the things. The power electronics can be broadly considered into various categories like this: DC to DC converter, AC to DC converter, DC to AC converter, AC to AC converter. But we are focusing on DC to AC converter, to convert AC to DC. So major power control applications, those converts include high and medium voltage drives application, then flexible AC tracks they are using it, active power filters, then reactive power compensation, renewable energy. DC indicators are widely used in control of drives, which constitute around 60-65% of total load on the electrical energy distribution. The main two inverters are voltage source inverters and current source inverters. Even though we have worked in current source inverter before, but all the work here we are going to present is on voltage source inverter. So let us take a DC to AC converter, the basic DC to AC converter. If you see the normal that single phase half bridge converter, if you use it and switch it as a square wave, so this is also AC waveform. If you see here, this is an AC waveform. If you do the Fourier series, you have all the harmonics, right from the fundamental to 5th, 7th, all these harmonics are there. So engineers will always have a solution. So if you want an AC waveform, take this switching waveform, then put a filter, you can get the fundamental, mathematically correct. But if you want to put a filter which suppress from there to all the things, then the size of the cost of the filter will be much more than the inverter. So it is practically not feasible. Then power electronics people, they borrowed the idea from the communication people. Say we use PWM, pulse width modulator. The original square wave is chopped using a fixed frequency, high frequency triangle wave. So when you do that one, so there is a fundamental here. But the advantage of this one is the harmonics, the high order harmonics will be shifted to the carrier frequency side. And the more we use high frequency carriers, we can shift it to high frequency side. So what is the advantage? So suppose an inductive load, the impedance for high frequency is L omega n. So if this harmonics is present, the current drawn by these harmonics is as L omega n increases, the ripple current, the content will be much lower compared to the fundamental. So you will get a nearly sinusoidal current. This is an interesting idea. But the problem is how much high frequency we can use it, especially for high power application, medium drives application, we cannot go for very high frequency. Probably low power SMPS we can go for high power, high switching frequencies of kilohertz and megahertz. But high power application, this is not possible. At the same time, high power, especially traction drives, if you take, we require a nearly sinusoidal voltage waveform. At the same, we cannot resort to high frequency switching to improve to increase the efficiency, because we are be switching high voltage and high current there. There the concept of people thought out how is it possible to get a nearly sinusoidal voltage waveform with a stepped waveform. Then if you see, before coming to that one, I just introduced this one. What is the complete voltage space vector structure when you excite the machine with all the three phases with a square wave inverter. If you see here, the vector locations will be tip of the vector placed at the hexagon of a vector. Now we want a sinusoidal voltage. So for it to get a sinusoidal voltage, the combined effect of all the three phases should have a circular structure. And this circular is the maximum circle which can be inscribed in the circle. Now to get a sinusoidal structure, let's the reference vector, the combined effect of all the three is here. This can be generated by switching between the adjacent vectors and the zero vector using volt-second balance. You can get anywhere in this sector. Similarly, other sectors. This is space vector PWM. We will not go much deep into the thing. This is already well known. Another thing, see, this is the maximum radius of the circle which can be inscribed in PWM mode operation. What we know in inverter, to get the maximum DC link utilization, that means we have to get the maximum fundamental voltage at the output for a DC link voltage. We have to go into a square wave mode operation in a two-level inverter. That is, when we go square wave means in a space vector, every 60 degree, the vector will be moving from here to here. So as it goes from the linear modulation range to the extreme modulation range, slowly the fifth and seventh order harmonics will get introduced. So many times, we may have to go to this region when, suppose there is a DC link fluctuation. So the fundamental should not suffer. So we have to move from here to here. So here it is, if you say 0.577 VDC, VDC is the radius of this hexagon or the DC link voltage, this will be 0.637 VDC. So this much range we can get, but we will introduce fifth and seventh order harmonic. Then many times in drives application, during the flux weakening region, we are going to the max extreme voltage range. Extreme voltage range, 6-step mode, we have to stay there if you want to get it. Then we have to run the machine, but with this much amount of fifth and seventh order harmonics. Can we have a inverter circuit wherein we can increase the linear modulation range from here to here without increasing the machine rating, that is a DC link voltage. At the same time, can we suppress all the fifth and seventh order harmonics? That is called increasing the linear modulation rate to the full base speed. We have recently come out to some of the idea for some of the multi-level topologies. So we will be talking about one topology now, later. So let us see the multi-level topology. The two-level, see, when I started my career in PWE, career as a research engineer from electrical engineering, we have to do the inverter using thyristors. That time power MOSFETs or power transistors are not, it's about to come. So initially we start with thyristors. Thyristors, the problem is we can turn on easily. If we turn off, we are required external force commutator circuit. So the inverter circuit will be big size. And is costly also because you use LC commutation. Those days, most of the research were, if you see, there is a lot of papers you could see on commutation circuit, how fast you can, how efficient you can do commutation circuits. Then the power transistor came, power MOSFET power transistor came. Before that, GT also, during that GT, now GT people are not using. But we will, how to get a multi-level structure. See, if you see here, this is the A phase. A phase, this is the pole. This pole is, it can connect here, it can connect here, connect here. So each connection we get 3 levels possible. So instead of 2 levels, 3 levels is possible. If you can have a 3 level like that, the PWM can be between the adjacent levels, we can switch it. So the dV by dt compared to a 2 level where we have to do the switching from here to here can be avoided, and at the same time harmonic content can be reduced. So this, when this circuit, in the first circuit came from a Japanese, from the Japanese people, we'll come to that one. Then 3 level is possible. Can we have a 5 level? 5 level means same using the previous schematic. See, we have 4 power supply, 0 is another level. So 1, 2, 3, 4, 5 levels are possible. By proper switching, we can have connect the A phase or B phase or C phase to any of these points. Then when you do that one, see the 5 level structure is like this. So the dV by dt is reduced. So if you can say the levels become smaller and smaller, that means more number of levels means we get an output average sinusoidal waveform, switched waveform very close to a sinusoid. So that is the idea. So how to realize such a circuit? See, this circuit, this is the one first 3 level circuit came, but initially this here in the place of diode also it was a transistor switch was there. It was first proposed by the famous Japanese group. This you know it. If these two are switched, this point will be connected here. If these two are switched, this point will be connected either depending on the current direction here or depending on the current direction it will be here. Off, this is off and these are turned on, it will come here. So 3 levels are possible. So this is still the most popular circuit for a medium voltage drives application. This is proposed by the famous Japanese people Akagi, then Nabe, Akagi and Takahashi. Takahashi is no more there. He passed away with in a car accident. This is one of the most popular. When this circuit came, I could see in many discussions people used to say 2 level is working very well and you are introducing more number of switches. More number of switches means more number of connections, more number of wires. So more number of di by dt, reliability and gate drive is required. That was the first reaction came. Because those days, almost all the inverter circuits were realized with discrete components. Now you could see, you could get all these 6 switches including the diode in a one semiconductor block. Those days it has discrete components. So this connection, it required different wiring, correct? More number of wiring means more number of leakage inductance, more di by dt. That was the first reaction to that one. Then the French people came with another circuit. This is by a very famous Frenchman. His name I forgot, still remember, I know this flying capacitor topology. I have met him many times. See, he told me, Maynard. I talked to him many times. I asked him how you came out this idea. He said, once there is a famous conference, IAS conference was in Japan. Though his professor Foch also went there. So this, they presented the 3 level circuit. And they said, they showed the practical results. So he came and told him, see, these inverter things are changing, new topology is coming. So he told him the dictates. Even he was discussing, he tried to figure out the circuit and finally came out with this one. He thought that is a circuit. So what he did, there's a charge capacitor. This capacitor he will place along the flow of the current, against the flow of the current, so that way you can balance the capacitor current and you can get 3 level. If this is VDC, this capacitor will be charged to VDC by 2. Let us say pole voltage. These two will connect means it is VDC. But if you connect through this way, it is VDC by 2. So if the current is in the direction, capacitor will discharge. But again we can get VDC by 2 putting through this way, diode it will go. So you can get capacitor by keeping and against the flow of the current, you can have the control and you can get 3 level here. But this, I don't know, not very popular, but Alstom still use it in their battery charger for their traction drive. I don't know, any other place with a multi-level this structure has extended, I don't know.
I think Anubrata they worked a lot on that.
This one. But okay, literature is there, but on practice, I don't know flying capacitor. But Alstom they use it because that is from the French side. So flying capacitor material topology. Then with the different power supplies, this cascade edge bridge is used to get multi-level structure. That every phase you should cascade many number of power supplies. As more number of cascade edge bridges comes, this VDC will come. This independent voltage comes in, voltage magnitude will come down. So this is initially used in for HVDC transmission, high power HVDC transmission. This already experimented, it's available. But the problem here is we require many discrete power supplies. Then we were thinking, Why do you require more number of power supplies? You want to get stepped waveform. Why do you require stepped waveform? With all the stepped waveform, still the maximum voltage range is within the two-level inverter, 0 to 0.637. That's a fundamental voltage is still the same. Why do you require stepped voltage? So that the harmonics can be suppressed. Now the question is, if harmonics can be suppressed, can we do away with the active power supplies and implement it with a charged capacitor? Why do you require active power supply if it is supplying only reactive power? And in the process, if we can control the capacitor voltage, see, it will be only giving reactive power and we don't require active power supplies. So we came with a circuit. DC link is here. If you see here, this is the original NPC 3-level inverter. It is cascaded with a VDC by 4 H bridge. So this will have 5 levels are there. How? So this is the main circuit if you do here. It's a cascaded flying capacitor and a H bridge. This is VDC, VDC by 2, VDC by 4. If you see here, it has 5 levels possible. 0, VDC by 4, VDC by 2, 3 VDC by 4. Okay? Then VDC. VDC is the extreme case, so that is missing there. Yes, VDC is here. So here, if you see here, VDC by, let us take a case VDC by 4, pole voltage. This will give VDC by 4. Suppose current direction is in this direction, VDC by 4. And we swap between this one and this one. See, the current direction is opposite. Then we can have this VDC by 4, we can balance it. This is called the switching state redundancies for the same pole voltage. And this VDC by 4 can also be controlled by through this one. But this will discharge. This can be controlled by swapping between these two. So here we require a lot of voltage sensing. Capacitor voltage is sensed. Try to control the capacitor voltage within plus or minus 5% of its nominal value. So if it is going above that value, at that switching period, switching instant, about the redundancies, appropriate redundancy will choose it, so that pole voltage will be the same. So for any level, all these levels we have redundancies. So the capacitor can be balanced instantaneously. This is run by Roshan here. See, this is the 5-level structure. See, current is sinusoidal, the capacitor is balanced tightly. And the capacitor can be controlled not only during steady state, transient condition also we can do. Sudden transient also it is possible. That means we are using a switch in a PWM cycle using switching state redundancy. We control the capacitor. So 5-level is possible, single DC link. What is the advantage of single DC link? We can get a 4-quadrant operation is also possible if this DC link is replaced by the front end control rectifier. That means direct power flow from the mains. So back-to-back power flow is possible. Then we don't require a DC power supply. The power comes from the mains. It is possible. Same converter can be replaced here. So then we thought, can we increase it to another level? This is a 9-level topology. This 9-level topology. If you see here, see VDC by 4 is shifted to here it's a VDC by 8. So this will have 9 levels possible, single DC link possible. And all the capacitor can be balanced. This is also reported work by Rajiva. It's already available. Then, okay, PhD has to continue. Then somebody came with it, can we have a increase the level to 17 level? Those 17 levels are possible. Then it is VDC by 16. The problem is, as you extend this one, this VDC will be very close to the drop across the device. So that effectiveness of this one will not sustain as you increase the cascading structure. So up to 17 level it came, then it's lot of structures are there, lot of components are there, but you will get a nearly sinusoidal voltage. So if you see here, the voltage and currents more or less sinusoidal. We are using stepped waveform, 17 level waveform we are getting. Then we came, See, if you see the A phase, you have VDC flying capacitor and 3 cascade edge bridges. So this can be modified. Then can we have instead of 7, 9 level? 9 level also possible like this. Here we found, these are symmetry here, here and here. So if you see the PWM level, if you say 9 level means 8 level shifter triangles are there. In this region 1, upper region, only this is working. In the lower region, only this is working. That means half of the time this is off, half of the time this is on. That's the advantage here. So how do you, in the upper region, this switch will be connected here permanently. In the lower region, this will be connected here. This is selector switch which selects between this upper block and the lower block. And the selector switch only works in a fundamental cycle. So if you see here the waveform, see this is the waveform, 9 level. Then we did one more thing. See, upper side this is not working, lower side this is working, but these two are the same thing. Say, can we have a common to both of this one with a selector? So we shifted the selector switch here. And the H bridge we made a common to that one. That is, during the lower operation, it will work like this. In the higher operation, it will work this way. So the number of power device can be reduced, and this can get a 9 level structure with the 2 DC links. Okay. So this is the capacitor, this is the capacitor voltage. And if you see here, this is the reference phase waveform, this is the selector switch. Selector switch works in a fundamental cycle. In the upper half, this is the PWM, the upper level will work. In the lower side, this part, this will work. The upper side will be clamped. So this way switching losses can be reduced. A 9 level structure we got it. The same thing can be used for on 17 level also. See, here if you see here 3 blocks are there. So in a fundamental cycle, this will work only 1/3 side, this side only 1/3 side, this will be 1/3. This is common to all by the selector switch. So this can have a 17 level structure. Now that the question is, we have independent DC link voltage. Can we have, we'll come to that one later. Can we replace this DC link with a charger capacitor and one DC link? Yes, it is possible. For that, we have to control the common coupling point fluctuation we have to control. We'll think about that one, discuss about that later stage. But this is a 17 level structure is possible. Yeah, this can also be done in a different way using MOSFET like this. 49 level structure that Ramu Nayar's brother Viju has done this one. And the space vector, okay, multi-level structure, before coming to multi-level structure, 49 structure also we have done. See, let us take another case, inverter operation. All this PWM operation, as the speed increases, the circular radius can maximum go within the inscribed circle only. Correct? That's a linear modulation time. But if you want to use the full DC link utilization to get a 0.637 VDC, then you have to work along this circle. But if you go from here to here, as I told before, slowly, 5th and 7th order harmonics will come into picture. So how to increase the linear modulation range to the full base speed without the presence of low order harmonics? That means we require nearly sinusoidal structure. We don't have to go to the 6-step mode operation. Sinusoidal structure without increasing the DC link voltage. At the same, that means without increasing the net voltage along ABC axis. Within the VDC available, how to do it? So this one student has come out with this idea. See, this is a 5-level circuit, open-end winding. We are using the concept of open-end winding. This idea originally came from Stemler in a EP paper, very vague paper. Myself and my guru, Ranganathan, was looking. He said, this is an interesting idea. Then we looked at it, see, what he says, we are using power devices, we have fast control. Why do you want to keep the neutral isolated? Originally neutral isolated because initially the induction machine was designed to operate from the mains. Mains will not be always sinusoidal. It has symmetry or unsymmetry happens, ripplant harmonics will be there. The moment ripplant harmonics flows, that will not produce a rotating MMF. That means there will not be a back EMF. So if any triplet voltage is there, it will produce large circulating current. So to suppress that one, the neutral are isolated. Now we can, neutral is open, we can feed from both sides. Lot of flexibility is there. So this is a 5-level structure. If you say this is VDC, this is VDC by 4, that is VDC by 2. This has, that is across the phase, you can have 5 level is possible. Then this maximum level in a phase is VDC. But we can also have VDC plus VDC by 4. That means one more extra level is possible. But the problem is when you make VDC, 5 VDC by 4, this capacitor keep on discharging. How to control it? What is the advantage if you want to do that one? Let us see. See, this is the structure. Original 5 level is here. 1, 2, 3, 4, 5. Now we put VDC by 4. So one more layer is possible. But the capacitor will discharge. So the required circle where we want to get PWM to get 0.637 VDC is within the PWM range according to this space vector structure. But the moment we go here, we are using VDC by 4, it will get, capacitor will get discharged. But along these points, that means all the points within the 5 level structure, the 5 level, the H bridges and all the H bridges can be controlled using switching state redundancy. That means every point there is a redundancy. Either we can switch this way or this way with the capacitor. The small capacitor can be balanced. That is the idea. So here what the student said, when we switch here, any reference vector here, we switch between this one and here. So here we are using VDC by 4. Here the capacitor will discharge. But during a sampling interval, we will be staying most of the time here and here. During this period, we can control the capacitor using switching state redundancy. So the VDC by 4, the current loss, the charge loss here can be stored here. When you do here, in this region, we will not be switching here. If you switch here, it has exceeded the VDC. So here, we will only use the triangle here. And here only we are triangle. All other sides equilateral triangle. This is an isosceles triangle for the PWM generation. Such that at any time when during a period overhead, we will not be, the component along the A phase axis will never go more than VDC. So when you do this one, here, see, if you the switching state redundancy, if you see here, different colors are used. So this colors according to VDC by 4, VDC by 2, if you see here you can see. Suppose if we want this location, here or this location, correct? See, by swapping between these two locations, see there is a opposite direction is there. So this capacitor can be balanced. By swapping between this one and this one, this capacitor can be balanced. So this is only for one location. Every location we have this switching state redundancy, the capacitor can be balanced. That's the idea. When we do this one, and this is a final space vector structure within which we are using the PWM. So we can get this circle. Increased linear modulation range is possible. See, this is the thing we got it. See, this has a 0.637 VDC. Originally, if you want to achieve this one, we have to go for the 6-step mode operation. See, we have a circular structure. See, fundamentally there, harmonics is suppressed. If you go there, all the 5th, 7th order harmonics are there. This extending the linear modulation range to the full base speed. We extended not only 5 levels, we recently extended to 3 level, 4 level, 5 level, any level it is possible. But appropriately, using an operator, you have to use the topology so that there should be a chance to recharge the capacitor. Using operator, we have come out that one. This is possible. Now it is, some level is doing by now, Rohit is doing now, correct? Yes. This is possible. Now the question is, later myself and my famous professor, very brilliant man, Professor Ranganathan, when we are sitting, we are discussing about, see, we always want circular structure. We are trying to get circular structure using PW using a hexagonal structure. Then we found, first time I was working on the split phase machine, that is in asymmetrical 6-phase machine. He first time drew the space vector structure. If you feed from 2 sets of ABC winding by 311, you will get a 12-sided structure. So if you see here, the first 12-sided structure, that is, instead of hexagon, 12-sided structure is space vector close to a circle. The first time this 12-sided structure is done by Professor V.T. Ranganathan. His original handwriting with notes is still with me. He told me, you come after lunch, we will discuss. See, this is interesting, there is a 12-sided structure is there. Then what I should do? You do the PWM instead of hexagonal structure. Use the same way. Use the PWM here. When I started analyzing, then I got the average pole voltage. They found it has a lot of 5th and 7th order harmonics. When you do the thing, same way do the thing. Okay, we'll come to that one effect later. Then I thought, what is the advantage of the 12-sided thing? 12-sided thing, if you know it, after the fundamental, 5th and 7th order harmonics are absent throughout. That means 5th, 7th, 17, 19, all that 6, n plus or minus 1, n is equal to odd number, all harmonics will be absent when you use such a 12-sided space structure for PWM operation. Then how to realize it for a 3-phase machine? Then we thought, we'll generate a 12-sided using open and winding structure. So I'll put VDC here, I'll put 0.336 VDC there. Then this is one part of a 12-sided structure. So 15 degree, next one you generate 30 degrees. So 12 into 30, 360 region will get 12 vectors. How you can generate this one? See, this is the 12-sided structure. What is the advantage? Instead of 6-step mode operation, you get a 12-step mode operation. So all the 5th and 7th order harmonics will be absent. How to generate that one? See, this is the space vector, this is the space vector. So every vector, we can put this one. These two are independent. While putting this one, you get a 12-sided structure. That is the advantage here. Then, see, you require 2 power supplies here. If you want to do 2 power supplies here. Correct? Instead of that one, can we do away with a 0.3 with a capacitor? So that this is the main power delivery inverter. The 12-sided structure can be anywhere. So what we found, if you take something like this is 90 degree. Then at this point, ideal case, if you keep the capacitor will not discharge. Charge discharge. In the cycle, in a fundamental cycle, the capacitor automatically get balanced, theoretically. But there is no vector here. We can only hexagonal vector. Then what we thought we'll do, switch average these two. So average vector will generate, switch and average vector 12-sided will be generated. Then by slightly shifting this way or this way, the capacitor can be charged, discharge can be balanced. That's the idea. See, this way switch average we got the 12-sided vector, and then the capacitor, while slowly shifting the vector this way, that way, the balance, exactly that position, the net power drawn is, real power is 0. In a fundamental 6 times it will be switching, the net power will be 0. But due to non-idealities, the capacitor can charge or discharge. That can be balanced by slightly tilting this way during the PWM operation. That is the idea here. So you see, you get a 12-sided vector. This is at 40 Hertz and 50 Hertz. 40 Hertz. See, the main inverter is switching with less switching. If this is the fundamental switching frequency here, the main inverter is, power delivery inverter is switching with less switching compared to the output frequency, but the most of the switching will be transferred to the switch capacity filter. This goes back and forth to control the balance. At the same time, the main driver inverter can go to 6-step mode operation also. Still, we get a current waveform which does not contain the 5th and 7th order harmonics. So the linear modulation range can be extended to the full 12-step mode operation. So at the same low order harmonics can be suppressed. See, this is here from the experimental result. So 5th and 7th are absent here. Here, see here, if you see the 5th and 7th is not there, next harmonics happens at 11 and 13. That way it goes. That's the idea here. See, 6 and 1 n odd, all the 5th and odd harmonics are absent when you say 12-sided polygon. See, if you can have a 12-sided polygon, can you have a multi-level 12-sided polygon? Then, instead of 2-level and H-bridge can get a 3-level structure. This is also a 3-level structure. So a 3-level structure can be visualized as a combination of 2-level structure with VDC by 2. So that means this is a 3-level structure which can be visualized as a combination of 2-level structure of half of this value, radius. This one, half of VDC by 2. So these two independent hexagons can independently produce a 12-sided structure. So a combination of the 12-sided structure will get a multi-level structure like this. That's the idea. Here also all the capacitor can be balanced. This is also we use switched average technique. See, this point is here also we realize switched average technique. See, this is the way for multi-level structure you got it. So the main power delivery is switching width less switching frequency. Most of the switching goes to the small inverter, the capacitor inverter, where it goes back and forth to control the capacitor balance. And inverter can go to the 6-step mode operation, square wave mode operation. That is main inverter 6-step mode operation. Even though it's a 3-level, the harmonics are suppressed here. So this is the switcher average. Okay, this is the computation for what are the things you require that one. You can go through that one. Then another student, my Bobby Matthew thing, can we get an 18-sided polygon? What is the advantage? 18-sided polygon means 5th, 7th, 11th, 13 are absent throughout. Correct? Then only you will harmonics at 17 and 19. 18 side means, see, this is possible. If you want to get this one, original, oh sorry. Original 2-level, that's a red structure, and on that one you superimpose the another hexagonal structure. Hexagon can be easily generated with a 2-level structure. If you do this one, we can have switched average at this point and we can get a 18-sided structure. So this is the circuit we used. This is multi-level. See, instead of 2-level, here also we used a 3-level structure. Here is also a 3-level structure. This value according to the vector we require for the 18-sided structure. Then see, we get, this is at 40 Hertz and 50 Hertz operation. See, the main inverter, if you see here, it is always working in a quasi-square wave operation. Most of the PWM is transferred here because it is suppressing the harmonics and it can go into 6-step mode operation. See, 18-step mode operation. And 18-step is a switched average mode we are getting it. So this is also a multi-level structure. What is the advantage? We are replacing the harmonics or removing the harmonics not with conventional LC filters. We are replacing with a switched capacity filter. A low volume, low cost switched capacity filter. So low order harmonics can be suppressed. At the same time, the main power delivery inverter can go to the full 6-step mode operation. So full DC-link utilization is possible. See the harmonics. If you see, this is the motor phase voltage. This is the primary inverter, secondary inverter. The harmonics of these two will be cancelled here. That's the idea. The switched capacity filter is oppose the harmonics here from the main inverter, and this nearly sinusoidal voltage you will get. This is the idea here. And we have come out with 24-sided also. This is possible. It can be extended to 24-sided. Multi-level 24-sided is also possible. See, this is a 25-sided with the single DC link and switched capacity filter. And we got a multi-layer 24-sided, 12 concentric 24-sided operation. What is the advantage? Throughout the modulation range, we suppress harmonics up to 17, 19 order. That is the idea here. See, if you see here, see. This is the harmonics of the main inverter. Then harmonics are suppressed here. So you get the. So the main inverter, even though 3-level, it goes into 6-step mode, square wave mode operation. See, the output phase voltage is a nearly 24-step. This various speed, you get a 24-sided thing. Is possible. Multi-layer operation is possible. Yeah, okay, we are going to 30-sided operation also. See, 30-sided also we extended this one. See, 30-sided means all up to 23, 25, all these harmonics are absent. And many multi-layer is possible here. Open and winding, small, low volume switched capacity filter. This is the standard 3-level structure. You get that one. Harmonics are suppressed there. See, this is the thing. In a square wave mode operation, the output phase is like this 30-step switched average, nearly sinusoidal current. And at the same time, we are not resorting to very high frequency switching for the main high power inverter. Then, so various speed of 45 Hertz. This is the thing. See, the main inverter, if you see here, it is slowly moving. Mostly in a quasi-square wave mode operation. It is not going to PWM mode. Slowly it moves out. Then another student, Rahul, thought, see, we talked about 18s. Can we have a power circuit which can be used for either 12 step or 18 step or 24 step or 42 step, a general circuit? The idea is like this. You have a main inverter for power delivery and a switched capacity filter. The power, if you see here in the output, the harmonics are suppressed because in a sampling depends on number of steps. In a 42 step operation, you get a 42 side, 24 step, 24 sided. So what is the idea? See, if we are using a 3-level structure here, and we don't want this main power delivery to resort to high frequency switching. That means we want only minimum switching possible. For a 3-level here, we are only switching either here, here or here. If you switch this one, this is the reference we want. There is an error here. Correct? This error we know the alpha beta value of this one we know. When we switch this one and or switch one, we know the alpha beta value or VA, VB, VC. So we can, by subtracting that value from here, we know the error value, what is the ABC. That error you feed it from the other side. So what is the advantage? Error gets suppressed. That depends on, and what are the harmonics suppressed depends on how much sampling you do it. So any number of samplings you do it, shifting the error to the other side, we can suppress the harmonics. That is the idea here. And if you see here, this is the main inverter. Main inverter is going to the square wave mode operation. See, this is the output waveform, this is the current. And then 30 hertz operation. See, it is going to the quasi square wave mode operation. That is, it is switching between the vertices of adjacent hexagons every second. So you get a nearly sinusoidal voltage. So throughout the modulation, it is possible. Then he extended this one, okay, 30 C4, 36 step to 42, 49, depending on number of samples you take it. You can have this one. Same circuit. And other side will act as the switched capacity filter. So depending on the sample, some of the harmonics can be. That means, depending on the samples, we are generating a switched average polygon along the vertices, in the space vector structure. And the error, due to the harmonics, due to the error will be fed from the other side, so that nearly sinusoidal voltage we get from the mains power delivery. This is the advantage here. He used a 6-level inverter other side, and that 6-level inverter can also be controlled by switching state redundancy, and also the main capacitor we can control by slowly adjusting the reference phase voltage. So the power can be reduced from the main, power can be increased from the thing. So machine, we have large dynamics, it will not be able to absorb that one. Depending on the capacitor, it will go to capacitor, capacitor will be discharged. So fast capacitor balancing is possible. This is the idea. Then, I think, how many more minutes? 1 hour only? How long? Another?
Timing is 1 hour.
Another how long?
10 minutes.
10 minutes, okay. Another student thought about it. So instead of switched average, can we get throughout the modulation range a stepped waveform? So we thought about, can we get a 24 stepped waveform throughout the modulation range? If the space vector structure has many concentric 24-sided, then we don't require PWM. As the speed varies, move from one concentric hexagon to other one. And 24-sided throughout you can get it. So to get a 24-sided, this is the 12-sided polygon generation. This already says, first you generate a 12-sided polygon. How to generate a 12-sided polygon, we already told like that. Then another more hexagon you superimpose. Both this original one, this one are independent. So we can get 24-sided. Cascading many hexagons like this, generating hexagons. So how to do it? So if you see here, the ratio required is here. Different, this radius and this radius has a relation. If you make the transformer isolation and the star data connection like this, we can get all the levels like this. This one will generate a 12-sided, independent 12-sided polygon from this side as well as this side, and one power input. We can do that one. So when you do that one, you get a this 24-sided multi-level space vector structure. Throughout 24 is possible. We don't require 24 steps, you don't require PWM. So in between you have to do PWM here because this difference is large. But a 24 multi-layer thing, it's possible here. Then, so this is the power circuit from this side as well as. All these voltages can be generated from a transformer isolation using star delta connection. Because these two are related to 1:√3. 1:√3 means the star delta 50 hertz, this is 50 hertz. Two layers are possible in the 50 hertz. Then see various speeds of operation. They 37.5, 10 hertz. They throughout everything is 24 step only. And there's a big done a vector control also like this. So all the capacitor can be controlled using switching state redundancy. So we got first time we got a multi-layer 20 step, 24 step inverter waveform. So this is the thing. It's this thesis. This is part of the thesis I have taken. So 25 polygon we have generated this one, and at present we are working on how to increase extend the linear modulation range for other multi-level inverters. So how to reconfigure the multi-level inverter so that using open-end winding configuration we can get the drive operate to the full base speed. That means without going to the 6-step mode operation, PWM mode operation, we can get 0.637 VDC equivalent to the 6-step fundamental voltage equivalent to the 6-step mode operation. Advantage is at the same time, in this case, in the extended linear modulation range or the region belonging to the over modulation range of the conventional inverter, the 5th and 7th order harmonics are absent throughout. We are still in the PWM modulation range. That's the thing we are doing now. Thank you. I'll stop here. Anything you want to ask? Any questions? I can ask. I think I took only 1 hour. No, I didn't. Okay. See, the polygonal vector structure, which I found it very interesting, which is the idea I conceived originally by Professor V.T. Ranganathan and myself. So we extended this to multi-phase drives. We have worked on multi-phase drives also. That we are not talked about that one here because our topic was only on DC drives. It's over the years by the first work on the multi-phase drive was with the Professor Joseph Videyathil, the father of power electronics from India, a great man. He built the hardware concept here. Then Professor V.T. Ranganathan came here. He introduced or encouraged us to work on high performance drives. Not only inverter control, because last time all these microcontrollers, 16-bit DSPs, more DSPs are microcontrollers, microprocessor DSP are coming. So a lot of computations were possible, worked on that one. So all these works are evolved through them, association through them. Later, I contributed or in incremental mode through the works of my students. Yeah. Okay.
Thank you, Professor Gopakumar, for this wonderful talk. The floor is now open for questions. So if anybody has any questions, they can raise their hands. And for the online participants, first of all, I would like to apologize because we couldn't get the laser pointer working. So I'm really sorry for that. So if you have any questions for the online participants, please type in. One of my lab mates will be reading it out and Professor Gopakumar will be happy to answer. So for the offline participants, does anybody has any question?
Online participants.
Very nice. Even Narayan also, my junior, he also got his PhD under great V.T. Ranganathan.
Yes. So I met him in 93, 94, 30 years now. Academic year 94, that's when he defended his thesis.
Yes.
So at the time, Professor Umanand, and there is one Zakaria Lakaparambi. All three were closing towards their PhD.
Yes.
And you are seeing both of them here, and Zakaria also finished, and he led a lot of national projects as part of CDAC, Trivandrum. And he's retired and he's some director of some college.
Yeah, that means what he started by Professor JV still continues here.
So that's there. And so 30 years is one man, I think his passion for research is not diminished. So that's Gopakumar.
Yeah, it's that if you say JV's thing with Mercury arc rectifiers, he started, then Tyrus came. The one he continued.
Correct. And then there were a few things I was always wondering, these ladies in South India used to do the rangoli, putting a lot of dots and connecting. I thought no electrical engineer can ever go close to that. Gopakumar challenged them and went past all that. And another one at high school, I was not very confident about polygons and polygons somehow becoming circles and all that. The polygon and circle again he mastered. And we used to think about 6 devices in an inverter as a big number for him. No, so many inverters and go on.
Yeah.
That's Professor Gopakumar. Thank you, sir.
Thank you.
Mind your business.
So, yeah. So before you wrap up, can you please have a big round of applause for the lab heads?
Thank you.